What I want to relate today is my experience, recent learning about building packages and for elliptic curves. So a little background to start. Sort of why I'm interested. Conic sections have been well understood for a long time. This is a modernized figure that Apollonius did in his work Conics back more than 2,000 years ago. And also we've known about solutions to the quadratic equation in the distant past, even before the algebra existed, to express it in this nice, neat, modern form. But an interesting aspect of conic sections, shortly after Descartes married algebra with geometry so that we could express curves as the zero sets of algebraic functions, the story was kind of completed for the conic sections. We can even find all the rational points on conics, and this is a classic rational parameterization of the circle. The basic idea is you start with one known point with fractional or rational coordinates, and you pick a point on the y-axis that's also rational, and that line intersects the curve in one other place, and that has to be rational too, because you end up with a root of a quadratic. If one of them is rational, the other has to be rational. So this accomplishment, with very little change in the basic concept, you can rationalize points on ellipses and hyperbolas, all the conic sections, creating a map essentially from Q to the rational points on the figure. And that's sort of the end of the story. There's not much more to say about conics. They are completely understood from an algebraic standpoint. Cubic curves are much more interesting. The general cubic equation, of course, has more terms. And it took up until the 16th century before the equivalent of the quadratic formula could be figured out. This group of colorful Italian mathematicians of the early Renaissance figured out a formula for the cubic equation and the quartic equation. And you can see why it's a little harder than the quadratic formula. There's Mathematica's version of the cubic equation. And of course, it's hard to do that, right? And that's just the case where you have an equation in a single variable, or the curve y equals ax cubed plus bx plus c. So enter elliptic curves, really a 20th century invention, had to wait for the work of the 19th century analysts, Weierstrass being an important one. An elliptic curve is a non-singular cubic curve in two variables over a field. And the non-singularity, we'll see why it's important. It means essentially that the derivative exists everywhere, and we need the derivative in order to get the structure that we're looking for. So this is in the so-called Weierstrass short form. It turns out that under a suitable change of variables, the general equation can be transformed into that form that preserves the group structure. And when I teach this to undergraduates, this seems to provide intuition. The blue line is a regular old cubic curve. And what we're doing really is taking the plus and minus roots of the cubic. So the elliptic curve is a solution to y is equal to plus or minus the square root of the right-hand side. And so in Weierstrass form, it's symmetric about the x-axis. So what makes these things interesting? Well, first of all, I think the study of elliptic curves motivates the study of a lot of interesting mathematics. If you want to study the geometry, you end up in algebraic geometry and algebraic topology. If you want to study the number theory, you end up being driven into the theory of complex variables, complex analysis. But even more so, in my study of these interesting curves, they illuminate the deep connections between these diverse branches. And they give a concrete example, sometimes studying the topics, topology, algebraic geometry, algebraic topology. In the abstract can be difficult, but the family of elliptic curves gives us a concrete world to work in. Also, elliptic curves have a wide-ranging use in both pure and applied mathematics. There are cryptographic algorithms based on elliptic curves. They're used in the integer factoring algorithm. In fact, that's built into Mathematica. There's a Lenstra's elliptic curve integer factoring. And they elliptic curves, a certain form of them, were used in the proof of Fermat's famous last theorem. And elliptic curves continue to be an active area of research. The Birch-Swinnerton-Dyer $1 million prize conjecture is still out there, is a deep theorem about the structure of elliptic curves. And there's active research papers coming out frequently. So this makes these curves interesting to me, both as an area of study and as an area of motivating undergraduate research. So what makes them different? Because of the structure of an elliptic curve, even though we cannot easily find the rational points, in fact, that's one of the hard problems, we can do an algebra of points by defining the sum of 2 points on a curve to be the reflection, essentially, of the third point of intersection of the line between those points with the axis. So if I back this up a little bit, we have points P and Q that you draw a line through them. The third point of intersection isn't the sum, but it's the reflection of that point about the axis of symmetry that's defined as the sum. And when you do that, it turns out you get a group structure with a little bit of extra work. But what about adding a point to itself? Well, that creates a slight challenge. If I can get these to line up. Yeah. How do you add a point to itself? Well, you don't have a line anymore, but you use the tangent line. And it turns out that even when you're not working in the Cartesian plane, you can still algebraically do a formal derivative to construct a tangent line. In this case, the tangent line is counted as a double point of intersection, and then you have the intersection of the tangent line is a third point, and you reflect it, and you get P plus Q. So that's the geometric idea of adding points. But to complete the picture, to get a real group structure, we need to look at projective space. So the idea basically is you convert your cubic polynomial to homogeneous form, which means introducing a new variable so that the powers, the total degree of each term, is the same. And then if you let that newly introduced variable z be 1, it's clear you get the original curve back. So all the points with coordinates x, y, 1 correspond to the real solutions in the original equation. But you get a new point, a single point that satisfies the equation where x is 0, y is anything, and z is 0. And that's the point we call the point at infinity, and acts as the group identity. So when that's done, we now get a algebraic group structure where this is the identity. It's not too hard to see that it's commutative because the line through 2 points is the line through 2 points no matter which one I take first. We have an identity. The inverses are shown in this picture. P and minus P are inverses because when you add them, you get to this point at infinity. And associativity works too, although it's hard to see. But the beauty of it is, even though this law was derived geometrically, it has an algebraic form of the addition law that's valid over any field, including fields where there's no visual representation of the curve. So there's the algebraic form. We're adding 2 points, we compute the slope of the line, change in y over change in x, where the y's are different, where the x's are different, and we use the implicit differentiation to get the slope in the case of a tangent point. And then the second equations there give the coordinates of x and y of the sum in terms of those things we just calculated. Well, surprisingly, that can be proven algebraically to give an abelian group. It's closed in the field. We have an identity, we have inverses, we have associativity. And so this is where elliptic curves get interesting, is we can now apply algebraic ideas to the geometry. So the purpose of the package I built is to provide a set of utilities or basic support over the standard fields, the rational numbers, the real numbers, the complex numbers, prime fields, and the general finite field, where I provided an overloaded circle plus operator to signify the addition of points, and an overloaded circle times operator to to signify the integer multiplication. And I chose this over overloading the regular times and plus in Mathematica because we're not in a field. What we really are working in is a group, which of course has a representation as a Z module. So it was I thought it was more appropriate to use these symbols for point addition and integer multiplication, which simply means adding a point to itself over and over again. We provide the ability to determine the order of a point. That's in the usual sense. How many times do I add a point to itself before I get back to the identity? Code to provide a solution to the discrete logarithm problem. This is known to be a hard problem, and the algorithm here is a standard one, so it's not good enough to break cryptography schemes with. And also some routines that support cryptographic and number theoretic applications. But the idea, I've been working with these curves for a while and I've written a lot of code. This was an effort to start to consolidate this into a shareable package. And Mathematica's ability to do arithmetic over, well, many different fields, particularly its ability to do modular polynomial arithmetic and modular polynomial algebra, makes it well suited to research in this area. So what have I provided? The basic design is there are two data types introduced in the package, an EC curve with 3 arguments, A, B, and F. A and B are the parameters of the curve, and F describes the field that we're working over. And there's also a new data type or a new head, EC point, which is used to represent the individual points on the curve. One of the key functions is setting the current curve, set EC with a curve, establishes the currently active curve, and now we can work in a very simplified form. Since the curve is implicit, we can use operator notation to do the elliptic curve arithmetic. And the underlying code is field neutral, and then hidden private functions take care of the dirty work of working in different fields. One of my design choices was for fields of prime order, the arithmetic is essentially just modular arithmetic, and so I implemented special routines to do that rather than using the finite fields package, just because it's a lot easier to deal with the integers than dealing with the GF symbols in a finite fields package. But it works also, or at least should work, I guess, using the finite fields package to create points with coefficients in the finite field and parameterize the curve with parameters A, B in the finite field. If you probably didn't notice, but in the group law, all that's used is addition and multiplication. So just the field operations as well as the negation, additive inverse, and the multiplicative inverse. So the group law is valid over any field. And so with no change, the code works the same over R or a finite field. Okay, so some examples of how the package works. There's a definition of a curve over a small prime finite field. We define the curve and we can verify that it actually is a valid curve. We can define a couple of points and verify that those are actually points on the curve. We can determine the order, algebraic order of the points, that is what I have to multiply them by to get back to the identity. We can use this nice infix operator notation to generate a linear combination of points. This kind of setup is commonly occurs in algorithms for elliptic curves. We can figure out the J invariant for a curve. This is a invariant that identifies if two elliptic curves have the same J invariant, then there's a rational map that maps between one and the other, and the group structure of those curves is the same. I thought with the end of October coming up, that was a curious J invariant. I didn't plan that, but anyway. We can also determine the order of the group. There's a theorem due to Helmut-Haas that bounds the order of the group close to the degree of the field. In this case, it says that this order of the group must be between 657 and 763, and we can actually determine the group order. I'm using a fairly simple method to do this currently. Oops, got to execute the right thing. Yeah, so the actual order of this group, it has 754 points, including the identity. Okay, so this is all over a small finite field. Another interesting example, this back before Descartes, early mathematician by the name of Bachet, developed a duplication formula for points that satisfy that relationship, the difference of a square and a cube equal to a rational number. And so we can sort of duplicate his work, define the curve, define one rational point on the curve, and then double the points. That is, add the point to itself would be the idea in modern elliptic curve terminology. He wasn't thinking in those terms. But as you can see, using Mathematica's exact rational arithmetic, we can keep track of exactly what's going on. And it turns out that's important for an area of research looking at what's called the height of a point, which is essentially the logarithm of the worst case length of the reduced rational numbers involved. But since, again, Mathematica's nice symbolic capability, I can actually apply this doubling to an arbitrary point and get back, instead of numbers, get back a formula that's, well, one form of the formula that Bachet discovered back in 1621. So the point addition and the point multiplication also work symbolically with reasonable limitations. Okay, a cryptographic example. The El-Gamal method involves using a couple of simple multiples of a point. And again, with the notation that the package supports, this is the entire encoding process. We multiply an integer times a point, and also a point plus an integer times another point, where I find a random point in a random integer. Decoding works the same way. I do negative scale factor of a point. Again, that works over any field. And also do a point addition. And so what does this look like? I set up a field and figure out its order. And that order n, the number of points in this example, is an important parameter. I generate a public key. And the public key in this implementation, I pick a private number s, and then pick a random point and create s times that point. And s becomes the private key, and the 2 points become the public key. Those are distributed. The public key is distributed, and a message is read in, secret message. And then the encoding simply takes the message and applies the algorithm to it and produces point pairs for each numeric message that's encoded. And then, of course, if this was a cryptographic scheme, this would be what would be public. And any eavesdropper who tried to read this message would essentially have to get s back, the secret number s, which means they'd have to solve the elliptic curve discrete log problem, which is, as far as we know, hard to do over a sufficiently sized field. And then the decoding algorithm is applied and turning numbers back into messages. And this is the correctly decoded message. Okay. So this is version 1.0. As of 3 days ago, nothing worked, but that's the way stuff happens, right? So we now have a working package. Where I need to go with this to make it really useful is to provide support over the complex numbers. There's some functions, if you're familiar with, that are functions in the complex plane, the Weierstrass P function and its derivative. It turns out those are related by a cubic curve equation. Also providing some extra support for number theory research. The Weil pairing is, which maps a pair of points to a point on the unit circle. And right now I've got an implementation of Scoff's algorithm for determining the order of a group. It's not very efficient for very large fields. Many years ago, Elkes and Atkins improved Scoff's algorithm and to make this useful for people working at the cryptographic levels, I would need to implement that algorithm. So these are my prime references. If you're interested at all in elliptic curves and know nothing about them, Elliptic Curves by Larry Washington is a really gentle introduction. Sort of one of my goals is to implement most of the book in the package eventually, piece by piece. And then for the number theoretic side, Joseph Silverman's excellent book, Rational Points on Elliptic Curves. Those are my two prime sources. And that's all I have to present at this point. I wanted to leave time for questions. And I have one question for you. If you're interested in this area, I'm interested in what you'd like to see added to this package.